More about asynchronous counters. So it's a continuation of what we have seen in the past day, and there's a lecture which has been designed so that you can pause the video whenever you want. You can go back and recheck what has been taught till now, and you can hear it at your own convenience. So we'll start with a review of what we have seen till now. We have started with the timing sequence where we considered a 4-bit counting sequence. It started with 0 0 0 0, ended with 1 1 1 1. So we drew the timing sequence and observed one very simple thing. Q0 changes with every number, Q1 changes with every 2 numbers, Q2 changes once every 4 numbers, Q3 changes with every 8 numbers. So this is what we denoted in the last day as B0, B1, B2 and B3. And we also observed one thing from this, that is, whenever there is a falling edge in one bit, the next bit will change. Okay, so that's something we identified in every case. Q1 here changes or toggles, we will say toggles, when Q0 had a falling edge. Similarly, Q1 toggled again when Q0 hit a falling edge. Similarly, there were these many toggles. Similarly, Q2 toggled whenever Q1 had a falling edge. Right. And similarly, Q3 toggled whenever Q2 had a falling edge. So if you consider a 5-bit counter, there will be a Q4 or in the earlier terms B4, which will toggle once every 16 numbers. So we kind of built the circuit for that. We used T flip-flops because it was a toggle operation all the time. There was no particular additional operation to do. So today we will just see it once again based on a JK flip-flop. That is one very important feature of JK when compared to T is T is a particular kind of flip-flop where J and K are short-circuited. So when I give T equal to 1, it's equivalent to giving J equal to 1 and K equal to 1. So VDD denotes a defined voltage. Normally we denote 1 with VCC or VDD. That is, it may be 5 volts or 3.4 volts depending on what circuit we are using. Okay. Now one important thing to notice is for every clock input there is a circle in front. It means that it's working on a negative clock cycle, and since we are considering edge triggered flip-flops, the JK flip-flops we have seen here are triggered on falling edges. And this is a circuit we built eventually. That is, the first JK flip-flop will be triggered with the basic clock itself. Then in order to cut the frequency down and make sure that the next bit changes only when B0 falls, we have connected the Q of the first flip-flop with the clock of the next. And similarly we went on with this and we identified that Q0, Q1, Q2, Q3, or in other terms B0, B1, B2, B3 will follow the sequence from 0 0 0 0 to 1 1 1 1. And we also saw how we can build a down counter from this. That is, when we analyze the patterns, we found that in order to reverse the counting sequence, all we needed to do was complement each bit of the sequence. So we can simply take the output from Q complement of every flip-flop and you will get a down sequence. So we will have a slightly modified sequence here, not sequence, the circuit. So here what we have done is, instead of a falling edge triggered JK flip-flop, we will have a rising edge triggered or a positive edge triggered flip-flop. You can see that because there is no notch or a circle in front. That is, it's a positive logic. It's a rising edge triggered flip-flop. Okay, so if you want to use a rising edge flip-flop and still make it work for falling edges, what you do is you connect it to the Q complement. That is, whenever Q rises, Q complement will fall, and whenever Q falls, Q complement will rise. Okay, so earlier what we did was we connected the Q to the clock and made sure that whenever Q falls, C will have a falling edge, the flip-flop is triggered. Here, whenever Q falls, Q complement will rise and this will trigger the rising edge triggered flip-flop. So the rest of the logic is same, it's just a different way of doing things. So I think you can pause the video if you need and just see how it works. Okay, so I guess there is no confusion in this. So what if we want up and down together? So the answer is very simple. We know that the up counter will take the output from Q, down counter will take the output from Q complement. So if we want up and down together, all we need to do is sample the up count from Q and down count from Q complement. So just to remind you, this is derived from the circuit we just showed here. So it's a positive edge triggered flip-flop. So the output is taken from Q complement. Okay, you can maybe pause the video now and see the sequence which it generates. Okay, so I guess it's clear now. So where does this thing come to be of use for us? Normally counters are not used alone. They are combined with some other circuit that will use the counts which we receive from the counter. So there will be something called as a receiving circuit. Sometimes it has an enable input, that is only when there is a particular clock signal it will enable that particular circuit. So you need not go through that complexity, just remember that it is enabled only at some points of time. And if there are n bits of count, the n bits will go as input to some circuit and it will generate a particular output. So if you assume that the receiving circuit is a decoder, so what is the output going to be? So there are n input lines. Okay, so we forget about enable because it's a control signal, it's not exactly data. So there are n inputs, and for a decoder how many outputs will you have? You will have 2 raised to n. Okay. So when the input is 0 0 0 0, line 0 will be active. When the input is 0 0 0 1, line 1 will be active. For 0 0 1 0, line 2, and similarly it goes on till 1 1 1 1 where line 15 will be active. So if you consider the counter circuit giving input to this, at every fixed interval of time the count will increment by 1 and the corresponding line will go high or corresponding line will become active. So can you visualize the kind of output we are going to get? It will be like what we see in the decorative lights we put up during festivals. The lights will light up in a particular sequence. Similarly, one output channel will be high and it will keep on cycling throughout the output. So there is one simple example of where we use a counter. Sometimes we use counters to set delays, that is till the count reaches some particular point we will stop using the circuit. Okay. So now maybe you can pause the video and try to draw a circuit where the receiving circuit is actually a decoder, and you can maybe even restrict yourselves to 3-bit counters so that the output will be just 8 bits. Okay, so now we will look at one particular kind of counter which is actually similar to a 4-bit counter, but it's not going to count till 15. Instead it's a BCD counter, or something we call as a decimal counter. So the main feature of BCD is every decimal digit is replaced with its 4-bit equivalent. So if we consider decimal digits, we only have 0 to 9. So it will start at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and it will come back to 0. Okay, so what's the difference now? Earlier, naturally the count became 0 after it reached 1 1 1 1. But now 1001 will not naturally cycle to 0000 because the counter will give a value of 1010 next. Okay, so it's not a naturally designed counter like what we have done till now. Okay. So how can we do that? See, if you look at this, there is one situation where we have to manually or we have to reset the count back to 0. And which is the situation? Whenever the count reaches 10, that is 1010, we need to cycle it back to 0. Or in essence, whenever the count reaches 1010, we need to clear all flip-flops and make it back to 0. So that is what this is actually going to do. Again, a JK flip-flop. Both inputs are 1. Okay, bear with me, this image was taken from the internet, so it's not like how I draw it normally. Okay, and you can find some minor inaccuracies in this because it's supposed to be negative edge triggered. But anyway, we'll just consider the layout for the time being and go ahead with this. So what happens in this? The count will keep on increasing normally, and at some particular point, if you look at this, there is a NAND gate coming here. A NAND gate takes input from 2 bits, which all? One is x3 and the other is x1. So what happens when x3 and x1 become 1? At that point, NAND gate will suddenly give an output 0. Okay, so this 0 is going to come to all the clear pins of the JK flip-flop. And one more thing which you see here is there is a circle here. That means the signal is, or that input is activated whenever the signal becomes 0. So whenever NAND gate becomes 0, it is going to clear all the flip-flops. Okay, so what happens in this? Initially all the outputs will be 0 0 0 0, so there is no problem because NAND gate will give a 1. There is no clearing option. Then next becomes 0 0 0 1, 0 0 1 0, 0 0 1 1, 0 1 0 0, 0 1 0 1, 0 1 1 0, 0 1 1 1. So in all these situations, both x1 and x3 are never becoming 1. Okay, so you can say that the NAND gate is not changing its output at any point. So now we get 1 0 0 0, 1 0 0 1. In the next clock pulse, what happens? You get 1 0 1 0. Now what happens here? x1 now is equal to 1, x3 is now equal to 1. The NAND gate is having both inputs as 1. The output falls to 0. It suddenly resets the entire counter to 0. So before you can sample the output, the reset pin will work and the output clears back to 0. So any subsequent count is only going to start from 0. Okay, so this may take a bit of time to understand, but it's easy to understand if you draw the behavior and list down how the values of x0, x1, x2 and x3 change. Okay, so you can pause the video now, you can try out how it is. Okay, so I guess it's clear. And now we'll just have a bonus slide coming up. So I said in the last class that there is something called as an edge triggered flip-flop and a level triggered flip-flop. So level triggered is what we have seen the behavior till now, and there is something called as an edge trigger. Now this is one example of an edge triggered flip-flop, so don't worry, you don't have to learn the architecture by heart. So just understand what it is about. Okay. So here the CP is actually split into two parts, and there is an actual edge trigger circuit that is going to receive the D input and convert it to an SR input, and that SR is actually going to control Q and Q complement. So this is actually a positive edge trigger flip flop. So whenever the clock pulse changes from 0 to 1, the D will be propagated to the output. In no other situation will the output change. So if you change the value of D in between a clock pulse, there is no change which is going to happen in the circuit. Okay. So I guess we will stop here, and if there's any doubt, you can surely come and ask me whenever I'm available. So thank you for listening, and this is my first attempt at a video lecture, so hope you liked it. Thank you.